of subsets of X of subsets of X. Of subset of X. Of subsets of X. Then the pair X comma A. Then the pair X comma A. X comma A is called measurable space. Is called measurable space. Measurable space. It's called measurable. What is that? Unit 11. Abstract, abstract measure, abstract measure, and measurable functions. And measurable functions. Measurable concepts. Okay, let X be any set, and A is a sigma algebra of sets. Of set X is the pair X comma A is called measurable space. So in this case, the member of A are called measurable sets related to A. In this case, the members of A, the members of A, members of A are called measurable sets. Are called measurable sets related to A. Measurable sets measurable sets related to A. Measurable sets related to A in measurable space. In the measurable space. A measurable space. The measurable space. Good. Next. For example, for example, EG means example. If M is the class of all Lebesgue measurable, M is the class of all Lebesgue measurable sets. Lebesgue measurable sets. In R, then R comma M, then R comma M then R comma M. R comma M is a measurable space. Measurable space. A measurable space. A measurable space. So M is a sigma algebra here since M is a sigma algebra. Sigma algebra by previous theorems. Sigma algebra. Okay. Next. Definition 2. Definition. Definition. Suppose measurable space A, suppose A, suppose A is a measurable space. Measurable space. Measurable space. An extended real valued set function mu. An extended an extended real valued set function mu. Set function mu. Mu. Set function mu. Real valued set function mu. Defined on A. Defined on A. Defined on A. Defined on A. Then A is called positive measure. Then A is called positive measure. Positive measure. Briefly, a measure. It satisfies the condition. Briefly. Briefly. A measure. Satisfies the following condition. Briefly. Satisfies the following conditions. The conditions. Conditions. What is the first condition? Mu of pi equal to 0. First condition is mu of pi means null set equal to 0. Second one, non-negative mu of A is greater than or equal to 0. Non-negative. Non-negative. Mu of A greater than or equal to 0. greater than or equal to 0. For all A belongs to script A. The pairwise disjoint sets, no, A we have mu of we have mu of union of n equal to 1 to infinity, union of n equal to 1 to infinity a n that equal to sigma n equal to 1 to infinity 1 to infinity mu of a mu of an mu of an mu of an mu of an. Thus non-negative set function thus non-negative non-negative set function non-negative set function mu defined on sigma algebra defined on sigma algebra sigma algebra sigma algebra A of subset of X A of subset of X subset of X subset of X A of subset of X such that mu of pi equal to 0. ST means such that mu of pi equal to 0. Mu of pi equal to 0. Mu of pi equal to 0. And having the countable additive property and having the countable countable additive property is called measure of countable additive additive property is called measure of x comma a. Measure of x comma a. So definition. One more definition. Definition. If x comma a is a measurable space and mu is a positive measure, if x comma a is measurable space, measurable space, and mu is a positive measure, mu is a positive measure, on it, then is called measurable space, measure space on it. Then Then X A mu, X A mu is called measure space. Is called measure space. Called measure space. It's called measure space. Called measure space. For example, EG means example. X mu m is a measure space. R R m R m is a measure space. Measure space. Measure space. Where m of e m of e where m of e is a Lebesgue measure of is the Lebesgue measure of Lebesgue measure of the Lebesgue measure of is a Lebesgue measure of E belongs to E belongs to M. E belongs to M. E belongs to. Okay. Based upon this conception, we'll discuss here. Page number 2, part 2. Part 2. Theorem. 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 Suppose X A mu is a measure space. SP means question formation is show that or prove that. Suppose X A mu is a fan. X A mu is a measure space. Is a measure space. X A mu is a measure space. Measure space. M is a measure space. First condition. If A belongs to script A belongs to script A, B belongs to script A, B belongs to script A, and A subset are equal to B. A is subset are equal to B. Subset are equal to B. A subset are equal to B. Then mu of A, then mu of A is less than or equal to mu of B, less than or equal to mu of B. Second, if AI belongs to script AI belongs to script script A. For I equal to 1 to 3, for I equal to 1 to so on. Then mu of mu of union union of I equal to 1 to infinity, union of I equal to 1 to infinity, AI yeah, is less than or equal to I equal to 1 to infinity, I equal to 1 to infinity, mu of AI, mu of AI. Yeah. Proof, important theorem for short answer type, 6 marks question. First one, since B equal to A union B minus A, since B equal to A union B minus A, A union B minus A is a disjoint union of is a disjoint disjoint union of disjoint union of A belongs to script A, A belongs to script A, and B minus A belongs to script A, and B minus A belongs to script A, script A. So that mu of B equal to, that implies mu of B equal to mu of A, mu of A plus, here union is there, that's why plus here. Suppose here intersection multiplication will come. Mu of B minus A, mu of B minus A, mu of B minus A. Therefore, either mu of A or mu of B is plus infinity. Therefore, either mu of A or mu of B minus A, mu of B minus A, B minus A is plus infinity, is plus infinity, plus infinity. Then mu of B, then mu of B is also mu of b equal to plus infinity equal to plus infinity. That mu of b is greater than or equal to mu of a. Thus, mu of b is greater than or equal to mu of a. So, mu of a. Mu of a. So, otherwise, both mu of a and mu of b minus a are finite. OW means otherwise, both mu of a and mu of b minus a, mu of b minus a are finite, are finite, are finite, and then mu of b, and then mu of b minus mu of a, mu of b minus mu of a, b minus b equal to mu of b minus a, mu of b minus a greater than or equal to 0, greater than or equal to. Proving mu of b is greater than or equal to mu of a. Proving mu of b is greater than or equal to mu of a. Mu of a. Second, given AI belongs to script A, given AI belongs to script A, AI belongs to script A, AI belongs to script A, AI belongs to script A for I equal to 1, 2, 3, so on. Right, BI equal to AI, right, right, BI equal to BI equal to AI minus union of I equal to union of I equal to I minus 1, AI, A suffix I. Then BI subset AI. Then BI is subset AI. 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 Subset AI for I equal to 1 to n. And BI are pointwise disjoint family of sets. For I equal to 1 to n. So on. And BI are pointwise disjoint family of sets in A. BI is pointwise. PT means pointwise. Disjoint, disjoint. Family of family of sets in A. Family of sets in A. That such that such that u union I equal to 1 to m union I equal to 1 to n I equal to 1 to n union of 1 to infinity I equal to 1 to infinity bi that equal to union of 1 to I equal to 1 to infinity ai. Therefore, by countable additivity of mu, therefore, the countable additive additivity additivity countable additivity of mu, we have countable additivity, we have mu of union I equal to 1 to infinity ai equal to mu of union of I equal to 1 to infinity bi 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 that equal to sigma I equal to 1 to infinity sigma I equal to 1 to infinity mu bi mu bi mu bi mu bi is less than or equal to is less than or equal to sigma I equal to 1 to infinity 1 to infinity mu of ai mu of ai mu of ai since since mu of bi mu of bi is less than or equal to mu of ai mu of ai. So remark, huh? The property proved one of theorem one is called monotonicity of mu, while that two is called the countability additive of mu. Okay, we'll discuss one more theorem. No, short answer. This theorem is for long answer. Page number 3, theorem. One more theorem. 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 Now, question formation is show that or prove that Suppose show that or prove that. PT means prove that. Prove that. Suppose XA mu. Suppose SB means suppose X A mu. What is this? Measurable space. Measure space is a measure space. Measure space. A measure space. If AI belongs to capital A, AI belongs to script A, script A. For I equal to 1 to 3, for I equal to 1 to 3, so on. Mu of A1 less than infinity, mu of AI less than infinity, and A I plus capital I for I equal to 1 to infinity, 1 to so on. Then show that, sometimes then show that here question formation. Then limit, then show that or prove that in here. Question formation will come. Show that limit n tends to infinity, limit n tends to infinity, mu of an, mu of an that equal to mu of intersection I equal to 1 to infinity, 1 to infinity, ai. So proof, proof. Proof. That a equal to intersection I equal to 1 to infinity ai, that a equal to intersection I equal to 1 to infinity, 1 to infinity, ai, ai. Bi equal to and bi equal to ai minus ai plus capital I, ai plus 1, I plus 1, I plus 1. So I plus 1 for I is greater than or equal to 1. Then bi belongs to script I, bi belongs to script I, 58. For I twice, A is greater than or equal to 1. Then Bi belongs to Bi intersection Bj, Bi intersection Bi intersection Bj is null set. Okay. Bj equal to null set means empty set. Empty set. For I is not equal to j, I is not equal to j, not equal to j. That is, Bi are pairwise disjoints and Bi are pairwise disjoints pairwise disjoints pairwise disjoints and pairwise disjoints and union I equal to 1 to infinity, union I equal to 1 to infinity, Ai equal to A1 minus A. Right? Verified. So therefore, by 3 of definition 2 we have, by definition we have by definition we have V of AI A1 minus AJ, V of A1 minus AJ equal to mu of union input I equal to 1 to infinity Bi union of I equal to 1 to infinity Bi that equal to sigma I equal to 1 to infinity 1 to infinity mu I Bi equation number 1 mu of Bi equation number 1, right? So A subset AI plus 1, since A subset AI plus 1, A plus 1, subset AJ, we have got subset AI, subset AI, subset AJ, subset AJ, subset AJ. So we get mu of A is less than or equal to get mu of A, mu of A is less than or equal to mu of AI plus 1, mu of AI plus 1 less than or equal to mu of AI less than or equal to mu of AI is less than or equal to mu of A1 A1 less than infinity, then infinity, less than infinity. Therefore, mu of A1 equal to, therefore, mu of A1 equal to, therefore, mu of A1, mu of A1 equal to mu of A union A1 minus AJ, A union A1 minus AJ, AJ, that equal to mu of A, mu of A plus mu of A1 minus A and, and mu of AI, mu of AI, that equal to mu of AI plus 1 plus 1 union AI minus AI plus 1 plus AI plus 1 plus 1, that equal to mu of AI plus 1 I plus 1 union BI union BI, that equal to mu of AI plus 1 plus 1 plus mu of BI respectively give respectively. It gives us mu of A1 minus A of A1 minus A1 minus A, that equal to mu of A, mu of A minus mu of A1 minus mu of A, mu of A, equation number 2. And mu of BI, mu of BI, mu of BI, that equal to mu of AI, mu of AI minus mu of AI plus 1, I plus 1, equation number 3. So from 1 to 3, we obtain from equation number 1 to 3, we obtain we obtain we obtain we obtain from 1 to 3 object. mu of A1 minus mu of so from 1 to 3 equations we get mu of A1 minus mu of mu of A1 minus mu of minus mu of mu of A1 minus mu of that equal to sigma equal to 1 to infinity mu of A minus A minus mu of I plus 1 mu of I plus 1 I plus 1 that equal to limit n tends to infinity limit n tends to infinity no limit n tends to infinity and then I equal to sigma I equal to 1 to infinity mu of A minus mu of I plus 1 that equal to limit n tends to infinity, limit n tends to infinity, mu of A1, mu of A1 minus mu of AN, minus mu of AN. Okay, okay. This implies mu of A equal to, this implies mu of A equal to, mu of A equal to. Limit n tends to infinity, limit limit n tends to infinity, limit n tends to infinity, mu of AN, mu of AN. Since mu of A1 is less than infinity, since mu of A1 less than infinity, less than infinity, hence prove is long answer type 10 marks important. Hence prove. So, more definition. Measurable functions. Okay? Measurable functions. Theorem number is Homer. HW means Homer. Okay. Definition. Measurable functions. Suppose x comma is a measurable space. It means suppose x comma is a measurable space. Measurable space. Measurable space. And f is an extended real value function. F is an extended real value function. Real value function. Real value function. Defined on x. Defined on x. We say that F is a measurable A measurable is 58. Measurable A measurable A measurable space and F is space and F is an extended real value in space are measurable with respect to A. Or measurable with respect to A. With respect to A means 58, that is 58. For every real number alpha, every real number alpha, the set X, the set, the set X is such that f of x greater than alpha, f of x is greater than alpha, belongs to script A, belongs to script A, to script A. So, zero, short answer type question. Zero, 3 and 4. Okay. Prove that every extended real value function, short answer. Prove that every extended real value function real value function, real value function means real value function, real value function on a measurable space. Fn means on ms means measurable space, x comma a, x comma, comma a is measurable, is measurable. Short answer question. Yes, is measurable. Yes, if f of x equal to minus infinity, so so if proof f of x equal to minus infinity for all x, for all x. Then x such that f of x is x such that f of x greater than alpha, greater than alpha, that equal to null set, means empty set. Alpha belongs to R, means real number. Yeah, real number. Shows that f is measurable. Shows that f is measurable. F is measurable. If f of x equal to plus infinity, plus infinity, for all x, for all x, then x such that f of x greater than alpha, x greater than alpha, greater than alpha, for the fact. For any alpha belongs to, for any alpha belongs to, uh, proving the measurability of f, proving the measurability of f, measurability of f. If f of x equal to c, means constant function. If f of x equal to c, constant function, for x belongs to capital X, where c belongs to c belongs to real number. Then x comma f of x, x comma f of x, such that f of x greater than alpha, that equal to pi, so pi. If c less than alpha, less than alpha, x if c greater than alpha, and in either case, the set either case, the set on the right is measurable, right is measurable, right is measurable. Therefore, f is measurable. F is measurable. Hence, proof. Thanks. Theorem number 5. Figure as one. Theorem 5. Now we discuss theorem 6. Theorem number 6. If F and G are measurable, then prove that or show that if F and G are measurable, measurable, then so on. Then prove that or show that F or G and F and G also measurable. Also measurable. Proof. For any real number alpha we have f of x, f x, f for v, for g, g of x greater than alpha, that equal to x such that f of x is greater than alpha, Union. Union. X such that g of x greater than alpha and, and x such that x such that f fund g when g of x greater than alpha, make it perfect. X such that f of x greater than alpha, union, intersection, intersection, x such that g of x greater than alpha. Now since x such that f of x such f for g x such that f of x greater than alpha and x such that f of x, g of x, g of x greater than alpha are both measurable, are both measurable, are both measurable, are both measurable. So we get that the sets uh, are measurable. So we get the sets x such that f for g of x greater than alpha and x such that f intersection f and g, f and g of x greater than alpha are measurable, are measurable, are measurable. Henceforth, henceforth. Okay. So what we discussed today? 11th unit, abstract measure and measurable functions. No, for definitions and three theorems. No, three theorems are taken as homework. So this is completed 11th unit. No, tomorrow we'll discuss about integration with respect to abstract measure. Okay, with respect to abstract measure. We'll discuss tomorrow. No, 12th unit. No, tomorrow we'll meet at sharp 3 p.m. No? Okay, I'm leaving. Thank you. Yeah, any doubts? No. Thank you very much. I'm leaving. Tomorrow we'll meet with a new chapter or new unit, 12th unit. Thank you very much. What we discussed, all exam point of view, most important. Thank you very much.